Okay, folks, here we are with our next video in our packet. We're moving on to integrals. We're going to talk about ways to approximate integrals by finding area. Okay, and I'm pretty sure a problem like this is going to be on here. The first way we learned to estimate area was by counting boxes, and the second way was by doing Riemann sums and trapezoids. Most of us do a Riemann, and there are what are called left, right, and midpoint Riemann sums. And remember, they're just little rectangles, and you're just going to find the area of each rectangle. So I'm going to give you an example of how we would do this and how this problem is going to come up on the test. Instead of giving you a function, they're going to give you a set of values, like so, over here. And they're going to ask you to find a certain Riemann. I'm going to graph starting on the left. The height of the graph is 2. Going over to there. The third one is this height. Going over to here. The fourth one is this height. Going over to here. The fifth one is this height, going over to here. You notice the last piece got left off. Okay? And when they do these, they're always not perfectly to scale. So what's going to happen is I'm going to figure out the lengths and the heights of each thing. So this distance is 1. I do it with arrows. You don't have to. This distance is 3. This distance is 6. This distance is 2. And this distance is 1. Then the heights, I'm going to write down in a different color. So the height of this one is 0. The height of this one is 4, 6, 2, and -5. And then I'll personally write down each of the areas of each one. So the first one is 0 times 1, which is 0. Put it over here. This one is 3 times 4. I'll usually fill them on in when I have them. This one is 6 times 6, which is 36. This one is 2 times 2, which is 4. And this one is 1 times -5, which is -5. So the area under the curve here would be 0 plus 12 plus 36 plus 4 minus 5, which you could do in the calculator and answer of 36 and 4 is 40, 52. 52 minus 5 would be 47. 47 would be the answer for that one right there. On a right Riemann sum, you would go in the other direction. You'd start at this 10 height right here and go this way, and you would leave off the 0. So let's just talk about what the midpoint would look like. They couldn't give me a midpoint of 5 rectangles. If they were going to do this, they'd give me a midpoint using... Okay, I think the one they're probably going to give you is the midpoint one. And for the midpoint one, they couldn't use all of these points. They would probably just give you these points here. And then say use a midpoint Riemann sum to find the heights of the rectangles. So basically what you would do is you take the first interval, which would cover 2 separate things, and you use the middle height to be the height of that. So it'll take, look here, I'm covering 2 separate ones. The middle of that is covering the height. I know it's not in the middle of the thing, but it's based on the middle of the points that we have. So the next one I would go between 4 and 12, and I'd use the height of 10 for that one right there. So the midpoint Riemann sum just uses the middle height on the questions right there. And so I have 2 rectangles. The width of this rectangle is 4. The width of this rectangle is 8. 8. The height of this rectangle is 4. The height of this rectangle is 2. So this one would be 16. And this one would be 8 times 2 is also 16. So the midpoint Riemann sum of this one will be 16 plus 16, which equals 32. I don't think they're going to do trapezoids. If we had to, the answers would be very similar. Let me just do the trapezoids up here so I can see them. Trapezoids are equal to 1/2 the base, sum of the heights. In which case, you're going to use every point. When I do trapezoids, I usually don't draw them out. What I do is I figure out each trapezoid, which would be from 0 to 1, 1 to 4, 4 to 10, 10 to 12, to 13. First thing I do is I figure out the widths of each one. So the first one is 1 unit wide. The second one is 3 units wide. The next one is 6 units wide. The next one is 2 units wide. And the last one is 1 unit wide. If you're not sure where I got those numbers from 1 to 0, 1 to 4 is 3, 4 to 10 is 6, 10 to 12 is 2, 12 to 13 is 1, and then it's the sum of the base of the two heights. So for the first one is going to be 2 plus 4, and then 4 plus 6, and then 6 plus 2, 2 plus -5 plus 10. With trapezoids, you always repeat a number in the column there, and then each one gets a 1/2 on it. And then I'd find each one individually because I'd have a calculator, add them all together, and that would be the area estimated by trapezoids. I'm not going to spend more time kind of going over those because we're going to do a bunch of them live because I know it's going to be there. The other thing that may actually happen on here is they may ask you to compare which one would give better approximations, left and right, midpoint and trapezoid, compared to the actual area of the problem. And I sometimes call them the lower Madel problems. It's really easy to know what's going to happen. Left and right always give the worst approximations of the actual area. Midpoint and trapezoid are better, and the actual area is always what's going to be in the middle of things right there. So to find where the R and the L go, I would just look at a picture, and I would draw a left. I'd take my curve, and I'd draw a left Riemann sum. This left Riemann sum underestimates the curve. That's why it's the worst approximation of area. And over here, that means right would be the... Sorry, this would be the biggest under-approximation. That means right's the biggest over-approximation. Come to this curve here. Look at this curve as it's drawn. I do a left Riemann sum, means starting at the left side. Underestimates. That goes... If I look at these last two, this curve here, if I do a left Riemann sum, it overestimates. That's why the L goes there. And same thing here, the left overestimates. So I literally find my L and my R where they go based on just looking at a picture of the graph. And then for the other stuff, it's all about the MUTMAT. If our graph is concave up, then it goes M underestimates, A is in the middle, and T goes right there. So concave up, I draw the mat because it's a MUTMAT. Concave also up, I draw the MUTMAT, and this would be the order in which these things will work. You find the things separately. If we have concave down, you don't have to rewrite it, but then it's the opposite of what it is. I call it tum-tam. If it's concave down, it's going to be the opposite order of what's going on there. I don't think we have to worry about that too much. I don't think it's going to happen that much on the actual test because it kind of is more of a multiple choice question, but we can see which ones approximate better than others. Okay, moving on with integrals, we're going to be using number lines again. When we did it with derivatives, f of x were the values of the graph, f prime were the slopes, and f double prime was the concavity of the graph. And we found our critical points where things change, and we could determine max and mins and poise based on changes there. When we go to integrals, they're most likely going to give us a graph of f prime of x. And with f prime of x, that means the values of the graph are f prime. And if I want to find the slopes of the graph, that's going to be f double prime. And the area under the curve, the integral of the curve, will actually be f of x. So how do we find those out as we're working? Well, one thing we do is we still build our same pieces of information, although we're going to do a f prime graph and f double prime graph. It's just how we look at the graph that's different. What I want to find on here when f prime is 0, I want to find where the values of the graph are 0. So it looks to me like that's at 2 and 4. So f prime is 0 at 2 and 4, and the values of the graph are positive, negative, and positive in those intervals. And I fill in my f stuff appropriately. I can't see it there. Along with that, I'm going to talk about it and how I graph it in a minute. And over here, my f double prime are going to be the slopes of this particular graph. Where is the slope 0? The slope is 0 here. And before that, the slope is negative. And after that, the slope is positive. Now the question is, how do I use that info to sketch a graph of f of x? Well, what I do is I make a set of axes, and I put my important points on there. 2, 4, and 3. So what I'm going to fill in first for f of x is I'm going to fill in some values for 2 and 4. I can pick any before that and afterwards. I can pick any starting point I want. Let's start way over here. According to my info, what happens is the graph, as we head towards 2, the graph is increasing, so the next point has to be above 2. Between 2 and 4, the graph is decreasing, So I'm going to put a point below it at 4. And after 4, the graph is increasing, so it's going to go up. I'm going to use a different color for my point of inflection. My point of inflection is at 3. So I just know halfway between there's going to be something happening with the graph as a point of inflection. And then all I'm going to do is follow my concavity information and connect the dots. So before 2, the graph is concave down. So I'm going to go down. Between 2 and 3, the graph is still concave down. At 3, it changes to concave up. And after 4, the graph is concave up. And that gives me what my graph looks like from there. And that sort of makes sense. F prime was x squared. So that means its integral is going to be 1 more. F of x is something like x cubed. Okay, take a look at the next thing. Drop to the top problems. You think they have to do with integrals, but they're really not. A drop to the top problem asks you to take the derivative of an integral. And when you take the derivative of an integral, all you're going to do is drop the number you have in there into the top, and it replaces what you have right there. So for example, for this function right here, if g of x equals this function, g prime, the derivative of this, is going to be f of x. We just drop the x into the top. The only time you have to do more is when what's on the top has its own derivative. So for example, on the second one, if I'm doing a drop the top problem, when I drop in the x to the 5th in for t, at the very end, I have to put its derivative on the outside, which is 5x to the 4th. It's very easy to identify these drop to the top problems because you will always be taking the derivative of an integral or the integral of a derivative. One way or the other, it's going to be a drop the top problem because there'll be a variable up on top of here. The only time where something like that has a variable on top and it's not a drop the top, it's literally just about finding area under the curve. So for example, if they gave me this graph right here, and they asked me to the function was equal to the integral from 2 to x of f of t, find all values of f from -1 to 6. So basically what I did first was I just broke this graph up excuse me, into little pieces of area, and I wrote down the actual values of the area. 0.25, 0.5, 1.5. And what you do then is you build the chart, but you figure out where to start. You're always going to start at the same number as the bottom. So if the bottom one was here, 2, the area between 2 and 2 is equal to 0 because you haven't gone anywhere. As you move forward, you add the numbers on you have. And as you move backward, you subtract the numbers off that you had because they're going in the reverse direction. So basically, if you look here, if I started at 2, between 2 and 3, there's 2 more bits of area. Between 2 and 4, there's that 2 and 1 more. Between 2 and 5, there's the 2, the 1, and the -1. And between 2 and 6, it's the 2, the 1, the -1, and the -1.5. Add them together, you get what's going on there. Because these ones are going backwards, we're going to do the opposite of what it says. From when I go from 2 to 1, I'm taking off 1.5. When I go from 2 to 0, I'm taking off the 1.5 and an additional 0.5. And from 2 to -1, I'm taking off all 3. And then you can come up with your numbers from there. And then if you want to check yourself, all you do is you start back at the beginning and you see if the numbers work. So when I started at -1, I had nothing to begin with. I picked a starting value of -2.25. So then I'm going to add this 0.25 and I get the 2. Then I add -2. I add the 0.5, I get -1.5. I add 1.5, I get 0. Add 2, add 1, subtract 1.5, and the patterns follow along. I'm fairly confident that on this page, that this is going to be one of the things they're going to ask us to do. It's kind of a highlighted problem. We'll work on that as we go forward. Okay, so in terms of integrating, I don't know how much they're going to ask you to do because you're going to have the rules in front of you right here. Integrating is the opposite of taking derivatives. And we'll go through the process of how we do a couple of basic ones as we go right there. We have all our rules for integrating, which are listed right here. You're going to have them with you. As a matter of fact, we're going to add a couple more in to here. Let me pause this for a second. Okay, we're going to add in a couple more we normally wouldn't add in. But just because they might come up, we're going to add them on in there. Just so you know, the integral of ln of x, you add these right on here, dx is equal to x ln of x minus x plus c. And we're going to add a couple more of the trig rules. Hold on. Trig integrals. Just because they may just put them there because they can. Here we go. So I know that the integral, these are extra ones that I'm putting off to the side, the integral of cotangent of x. Normally you wouldn't have to know these. Dx is equal to the ln of sine of x plus c. We're going to add in integral tangent of x dx equals negative ln of cosine of x plus c, and the integral of secant of x. Once again, I don't know if we're going to see these, but why not have them written down? It's equal to ln of tangent x plus secant x plus c. And if you could guess what the one is for cosecant, guess what it's going to be. Negative ln cotangent x plus cosecant x. So those are the other additional ones we have, along with the general rules. You'll have these in front of you, so you'll have them to work with. The one most people mess up is this one right here, a to the x. But now that we have it, we're good to go. So rules on taking antiderivatives, okay? So let's discuss it really quick. The whole thing is you have to set up this set of brackets for the derivative of the inside. You can't take the derivative. So first of all, if things are just separate like this, we're just using our regular rules of going up one unit and put the flip of the original out in front. So right here, just do each one of them separately. If you have something that's a radical, you're going to turn it into 1/2 power and go from there. So here's the example of where you're going to have to get the derivative of the inside written there. So if I look here, the derivative of the inside of this function is -3. That means I place a -3 on the inside, and I have to counteract it with a flip of it outside, -1/3, to give myself the answer that I'm going to want. It's only constants you're going to be counteracting. Anytime there is something like this one right here, where the derivative of the inside would be 6x squared. Well, I would have to have an x squared just lying around, which I do. I move that into parentheses. What do I still need? I'm going to write down what I need. This is what I need. I have the x squared lying around. I stick the 6 in, and I counteract it with a 1/6, and I have the answer right there ready to go. When integrals look like fractions, first of all, if the bottom is not to the first power, we're always going to bring it up to begin with. So I would rewrite this as something to the -6th power. The derivative of the inside is 5x to the 4th. So I'd have to have an x to the 4th just lying around, which I do. I add a 5 in. I include a 1/5, and we're good to go. The general rule is there's going to be a constant you're going to need, and the flip of it is going to be out in the answer right there. If your bottom is not to a power, then we're hoping it's an ln problem. So the first thing we do is take the derivative of the bottom, which would be 3x squared. Do I have an x squared lying around? Yes, I do. I put it in there. I still need a 3, so I add a 3 and counteract it with a 1/3. And look at what I'm left with, 1 over something. And the integral of 1 over something is the ln of something, plus 1/3. The other type, so really quickly, we have the list of trig derivatives, so we should be okay. And we use our calculator for them, so it shouldn't be a problem. The only one that can be a little tricky is if something is a 6 ticks problem, meaning its looks of the form. I'm going to flip back to it. It looks like it's one of these 3 problems right here, which you'll be able to see when you're on there. If it looks like that, we just need to get it to look exactly like that, which means I move this 3 to the outside and solved 1 over 3 sine -1. 3 inverse sine of x plus c. I don't think I need to go over these like crazy because we're going to have them in front of us. I don't think they get us to do a lot because we're going to have our calculators. The hardest one they could ever give, let me show it to you here, hold on, is right here. So I'm going to walk through this problem, and then I'm going to do one last question on here, and then we're going to be done for right now. This is the hardest the integration could be. This is page 24, which is it looks originally like this right here. Okay, so If you don't fully understand this when we're done with it, it's okay. I believe this is a 6 ticks and you're dead problem. I believe this is really of the form of something of 1 over square root of 1 minus something squared dx. All I have to do is get it to that format, like so, and then I know it's an inverse sine problem. So what I did first, yep, there we go. Let me see that? Yeah, we can. I moved the 7 outside, so I got the top of the problem looking correct now. Now, the next thing I did was I took this problem and I know I'm trying to get there to be a 1 underneath here. So what I did is I factored a 9 out of each part of those right there, because 9 times 1 is 9, 9 times 1/9 is that right there, so I now have that factored correctly. I then rewrote this problem. Instead of the 9th on there, I wrote it on the bottom of the fraction. And now this 9 right here can come out as a 3. And because it's there, it can then go out front. That's how I dealt with that 3 that was right there. So now I've got a 1 here that I need and a 1 here that I need. But now I need this right here in this form. And it is a something squared. So what I did is I took that 9 and I sucked it underneath the problem right there and put it to the squared power. So I have it right there. Now I'm ready to, oh, look, these cancel out. So for the 7. Now I'm almost ready to integrate. I need the derivative of the inside of this piece right here. So the derivative of that is 1/3. So I add a 1/3 to the problem. I put a 3 over 1 out there to counteract it. They cancel, and I'm left with this as an answer right here. A lot of steps for inverse trig, but here's what we don't care about. We're going to have our calculators. So if you take a look, when this inverse trig problem, the 9 that's there is a square that right there. 7 that was up top is now out front. So any problem can be solved like that without having to do all the steps. Any numbers here go out front. If this is a 16, it becomes x to the 4th on the bottom of the problem. So we can do that problem without having to go through all this. In the past, you had to figure out how to suck all those things out of the problem. Okay, last part for this video right here is sometimes you have to use the definition of the derivative, or the integral, to find area under the curve or to find a missing value. Okay, and it's not that complicated, but it's hard to identify when you're doing that. Remember, if g of x is equal to the integral of a to b of f of x, that means that the integral is equal to the g of the upper minus g of the lower, because it really means this is equal to g of x, because that's the integral of it from a to b, and then we plug those 2 points on in. So the area is equal to g of the upper bound minus g of the lower bound. We use that to find missing information. So it says given g of x is equal to the integral of f of x, so g is the integral of it, and g of 5 equals 10, find g of 0. That would just mean that the area under the curve from 0 to 5, we can see what it is. It's equal to f of x is equal to 12. So we found that area right there. But it's also equal to integral of f of x from a to b is equal to g sub a. So g sub x from a to b, which would be g to 5 minus g of 0. Well, they gave us the g of 0. We filled that on in. And to find the missing point, I just fill it into the equation. This is going to be there. I think it's going to be there a bunch. It just is when they give you an area of something and they're asking you to find a point, we're going to use the general rule of integrals to solve that on out. Okay, ladies and gentlemen, that's the end of this video. The rest of the stuff I'm going to do will be next video. It's going to be the last things on differential equations. We're not going to go crazy on it. And then a couple of the weird little rules that they might put on us. We'll talk about that in the next video, which will be the last one. Take care.